Continuing on in Chapter 9, we've discussed so far how we've gone from proportions to means, and we've discussed the sampling distribution for means. In this video, we want to refine the central limit theorem and adjust it for dealing with means. There are certain conditions that need to be met. If the following conditions for the central limit theorem are met, the sampling distribution will be approximately normal no matter the shape of the population distribution. So it doesn't matter if the population is originally skewed right or skewed left, or it's multimodal with all these different peaks. If we can meet these conditions, then the sampling distribution, which our calculations will be based off of, should be approximately normal. The sampling distribution of x bar of all those many sample means is approximately n. Mu is the population mean. And recall that this sigma over the square root of n, that is our standard error. Also, as we discussed, the larger the sample size, the better. Increasing the sample size is one of the best things you can do for your statistical study. The larger the sample size, the closer your sampling distribution will be to the normal distribution. So the central limit theorem conditions. Condition number 1, you have a random sample, just like we saw before in chapter 7 and 8. We also want to see independence, which we are going to assume independence most of the time, just like we did back in chapter 7 and chapter 8. So we're going to check that we have a random sample. We're going to assume independence. The second condition, do we have a large enough sample size? And this is where we used to check successes and failures. It's much more simpler in chapter 9. As long as the sample size is 25 or more, the distribution will be approximately normal. Some texts say 30 or more. Our textbook that we're using happens to say 25. So we're just going to make sure the sample size is 25 or more. We don't have to check successes and failures, so we need to make sure it's a random sample and we have at least 25 people or objects in the sample. And then finally, if the sample is done without replacement, the population must be at least 10 times the sample. We are going to assume this property as well. A lot of times we don't know if the sample is done with or without replacement. That's not mentioned in a lot of examples. And also we don't know the exact size of the population. So that can be difficult to check. So we're just going to make sure that we have a random sample and sample size is at least 25 or more. And again, the larger the sample size, the closer to the normal distribution. So these two histograms display that. This first histogram in blue, I have the value of the sample mean in dollars. In the sample size was 30. So we had sample after sample after sample, each of size 30 taken. And these were the results in the histogram. We see it is approximately normal. We've got this high peak in the middle, these tails that are fairly even on the left and right. It's not perfectly normal. The right tail seems to be just a tad longer than the left tail. There's this peak sticking out of the drawn in normal curve here, but it's approximately normal. On the right hand side, the one in orange, we've bumped the sample size up to 60. And we can see it fits under this normal approximation a little bit better. The tails are a little bit more even. There's not this large peak sticking out the top like there was on the left hand side. So the larger the sample size, the more normal your distribution becomes. Also note the one on the right with a larger sample size is narrower. This histogram only goes from about 2100 to about 2900. The one on the left appears to go from about 1900 up to 3100. So there's a larger range of sample means in here than in here. We're focusing in on the population mean more with a larger sample size. Example 3, we apply the central limit theorem and take this a step further. So it says the mean resting pulse rate of adult women is about 74 beats per minute with a standard deviation of 13 beats per minute. The distribution of resting pulse rates is known to be skew right. This 74 beats per minute is my mu. It says the mean resting pulse rate of adult women. It's not from a sample, but this is assumed to be about all adult women. And this standard deviation of 13 beats per minute, this is going to be sigma. It's assumed to be about the population. A says if a random sample of 20 women is taken, is the sample size large enough for us to use the central limit theorem? The answer is no. It is random, but the sample size of 20 is not large enough. We know we need at least 25. It's 25 or more. B remedies that. It says if a random sample of 100 women is taken, is the sample size large enough for us to use the central limit theorem? The answer is yes. We have a random sample. We have over 25 women in the sample. I'm going to assume independence. The population of women would be 10 times larger than the sample size. I don't know if it's with or without replacement. Not really a big deal for us. We do want to go a bit further and note, well, what would be the expected mean and standard error for the sampling distribution? Well, right off the bat, because the central limit theorem conditions are met, I know that my sampling distribution should be approximately normal. Focusing in on mu, which I know is 74. So my expected mean, right in the middle where the mean is 74. We just learned how to calculate the standard error in the previous video. The standard error is sigma over the square root of n. Sigma from the problem is 13 over the square root of 100, since that was our sample size. That's 13 over 10, which is 1.3. So I could go up 1.3, that will be 75.3. I could go down 1.3, that would be 72.7. And most of my sample means would be in between these values. Not every sample mean will be exactly 74. Some will be a little bit lower. Some will be a little bit higher. Most will be within 1.3 beats per minute of that 74